that people say that they liked reading a thesis, but I really liked reading your thesis for the reason that I think this is a very special PhD thesis, not only because it's very impressive regarding the amount of work. Okay. It's impressive regarding the amount of work that you have done, but also in the sense of the collaboration, because you both collaborated with people from industry, but also at the other end from people from the applied mathematics and the computer science departments. Right. So I think that is very good to bridge the gap in this field from the models towards the applications, and it's really needed in our field.
Thank you. Happy to hear that.
So I will start asking you questions.
Yeah.
We have had a pre-meeting.
Okay.
Me, Peter Svensson and Jonas Brunskog, and we will go by your studies.
Okay.
We'll start with the first study, and every time there's another of the members that starts with the questions, and then the others will add some questions to that to keep the discussion a bit alive and not too monotone.
Okay.
Okay. And then in between we will also have some more general questions because so that we are not asking too many details.
Okay.
So to start with the first study, that's on the spectral element method, the first paper. And well, I like a spectral method, so it's very good to see that you also tried such a method. My first question is actually, so a spectral element method, depending on how you choose your parameters, the order of the method and so on, it's actually a classical finite element method, right?
Yeah.
So when would you classify this as a spectral method?
To my understanding, it's at least when you have n equal to 1 basis functions, then the spectral element reduces exactly to the linear finite element method. But as soon as you go beyond that and use these types of basis functions, then this, to my understanding, is what would be called the spectral element method.
Okay, so it's related to the type of basis functions?
Yes.
Also to the order of the method?
Yes. Yes. So I mean, you can have a a low order spectral element method, but then it's equivalent to the final element method.
Okay, and is when you call something a spectral method, because there's more types of spectral methods, as you also have written in your introduction of of the paper.
Yeah.
So what is a property of a spectral method?
Isn't that the exponential convergence of errors when you increase the polynomial basis order?
Yeah. And
so I believe the classic description of, or at least I've read it somewhere, the classic description of SEM is that it combines the attractive geometric flexibility of finite element methods and the attractive error properties of spectral methods. And then you have the spectral element method.
Yeah. Do you have your thesis available?
Yeah, it's here. Should I open?
I will ask questions and they relate to it. So,
absolutely. Let's find paper 1 here.
Yeah, on paper 1. And when you start there, maybe you go to the next page of it. Yeah. So you start with those linear acoustic equations for pressure and velocity. Yeah. And then you write, well, it's equivalent to the second order wave equation. So you solve these equations and not that second order wave equation.
True.
And
maybe,
why?
Yeah. Well, I mean, they describe the same phenomena, right?
Yeah.
But I guess it's more straightforward to solve both with respect to time discretization and perhaps also the spatial discretization to solve first order systems. So that's the reason why we have gone with this approach. So I certainly the SEM method or DGFM or whatever can be used to solve the second order system, but yeah, it's a convenience thing, I guess, to solve the first order system.
Most people solve this, huh?
Yeah.
But is it somehow related to the boundary conditions?
It is convenient to know the particle velocity, which when you solve the second order equation, then you're only solving the pressure. So yes, in terms of the boundary conditions, it's convenient to know the velocity to compute the incorporate the boundary conditions. Indeed, that's another reason. Yeah.
And if you, let's see.
Moving on, yeah.
Yeah, go on. I'm looking. Somewhere you describe, so you have described your boundary conditions and how you implement that, and then you describe that you have a different way of solving the time functions, in the implicit way or the explicit way.
Yeah.
Can you explain that again to me?
Yes, yes. So we have this implicit, explicit time stepping method, and that's because we have we're solving two systems, one can say. We're solving the main system, which is this system here, and then we're solving this auxiliary system, which is the boundary conditions, right? And the stability criterion, we need a certain time step, as is described here in the discussion here, where is it? Here on the stability, we need to uphold a certain or have a maximum time step in order to preserve the stability of the simulation. But this is influenced by the eigenvalues of the spatial discretization, but also by the stiffness of the auxiliary differential equations. So what can happen is that you have these boundary equations, and they can, for some certain materials, be very stiff, which means that you need to restrict. If you solve everything explicitly, then you need to restrict the simulation to an unnecessarily small time step. Because what we want is to solve with as big of a time step. So this is at least. I mean, there are other ways of doing this, and I know Kuching, for example, he's taken a slightly different approach where he does a stiffness restriction, or he does the fitting of the material such that he ensures that the parameters of the auxiliary differential equation are within these stability criterions of the spatial discretization. Sorry, long answer here, but it's because then we don't see any problems due to the potential stiffness of the auxiliary differential equations.
Yeah, I think I get it. So you're finding for a way to reduce the stability constraint. Yeah.
So then the only stability constraint is the standard CFL stability constraint.
Yeah, I actually had a detailed question on equation 30. Yeah? So you have U and W. Are they coupled? And if so, how are they coupled?
Yes, I would say so from the top of my mind that they are coupled, because at the boundary, U is, if I remember correctly, I write U is the explicit part, so the main system, and then W is the implicit part, the auxiliary differential equations. And certainly the input to the auxiliary differential equations is the pressure which comes from this system.
Okay, yeah. If you go further down, then you have some figures. Figure 2 on the errors. So you also described what type of errors you have in your system, and it turns out to be only dispersion error if the CFL number is very low, right? Because then you only So does it mean that in these figures where you have a very the top one, with CFL a very low number, does that mean that this is actually only the dispersion error we are seeing?
Yeah.
Okay.
So there's, as is mentioned in the paper, it's been shown that SEM is only dispersive, not dissipative. So the only dissipative errors are due to the time stepping part.
Okay, then I have a bit more general question on applying this method and also this DG-FAM method you use later on.
Yeah.
You say, okay, if you use higher order method, we also saw that in your presentation, with a higher order, then you reduce calculation time because it has a better convergence rate. But if you would solve a room like this one, and you would apply a mesh, then you need small elements depending on what detail you decide to model. But if you have small elements, and you have the high order in those small elements, your time step gets very, very small.
Indeed.
So it's not as promising as it might look like in my perspective if you solve realistic rules.
It's a perfectly valid point you're making here. And in most of these cases I showed there were simple empty rooms, right? When you have detailed geometries, then you need typically smaller elements to capture them. So that's yet another kind of caveat. I mentioned those two caveats, right? You have more degrees of freedom in the elements and you need a smaller time step. But then the third caveat is capturing the geometry. I would say that DGFEM is perhaps better suited here because what you can straightforwardly do with DGFEM is that you can use different basis functions in different elements, straightforwardly. So you can have, for example, fourth order discretization here near these details here, and then up here you can have order 10 or 15 or whatever.
Can you?
Yeah, really so.
But if you have the fluxes in DGFEM, now we go to another paper, but I can ask that question. So you have to couple the elements.
Yeah.
But do the nodes need to be co-located?
I mean, I haven't tried implementing this, so I should speak with some caution here. But I don't see why you couldn't just interpolate to any point, you know, to get the value. So use interpolation. So I believe this has been done, to my understanding, to use different bases in different elements.
Okay, thank you. We move on.
Yep,
so if you go down, figure 3, you have again, figure 3 is again the dispersion error.
Yeah.
So that means that the sound is either leading or lagging the true sound.
Yeah.
But this is a one-dimensional calculation, and you say, okay, the same behavior will occur as in one dimension.
Yeah.
But will the magnitude of the errors increase, and do you have a feeling or an estimate on how much?
Yeah. I don't have a good feeling for how much, no, but I predict that the magnitudes of the errors will increase. So then you will get direction-dependent dispersion behaviors. And I believe, for example, in finite difference methods where you have a very regular grid, then you can analyze this quite precisely. But when you're working with unstructured grids and so on, then it becomes a bit difficult to do this three-dimensional analysis.
Yeah.
So I think this dispersion analysis is fundamental in some sense. It does, for example, the difference between low and high order and so on. I think that more or less holds when we go to 3D, but indeed the magnitudes of the errors might be different.
Figure 8, please.
Figure 8, yeah.
All right, so here, yeah, we see a very nice result where if you increase P, the order of your method, then the result is closer and closer to your reference solution.
Indeed.
Did you normalize both results to the source spectrum?
Yes, so the analytic solution takes into account the source spectrum.
Yeah, it takes into account normalization to the source spectrum.
Yeah, so it's not a flat spectrum, you know, case here. It is. It has this.
So then, indeed, it's not a. Then we cannot call it a transfer function. You also write frequency response, so that's fair. Yeah. Okay.
Good point. Yeah.
But in both cases, you have the same source spectrum.
Yeah.
But if you look closely, you see, okay, it gets much better, but still there's at some frequencies, you see some
for the higher
resonances that you don't see in the reference. For example, around 250 hertz. Is that noise, or is it an artificial mode, or is it caused by a small phase error? Do you have any?
No, I'm not sure. Yeah, I don't have a good. So there is absolutely nothing there in the analytic solution. Yeah, you can see it's a dashed line, but it goes a bit up here. So there is something there.
Yeah.
I guess if I would move the receiver a little bit, maybe this wouldn't be apparent.
Yeah, but it could be.
Yeah, the cause is not clear.
No, but it could be a numerical, maybe some numerical mode.
Yeah.
Or
yeah,
because it does not seem to be something physical.
No, no. Yeah, further analysis needed here, I think.
Very good. Let's see. I think I have one more question, page 92. On the, you do some equation 30. Oh, sorry, no. This paper. I wrote it down. That's from your thesis, yeah.
Yeah.
Equation 43. Yeah. So you somehow find to simplify it to speed up the calculation, and you say, where am I? Sorry, I'm looking at my questions. Yeah, so you have there the that matrix M, A, J,
yeah.
I, J. And it seems that you use the diagonals of it in your calculation. Does that mean that the values out of the diagonal have like such a low value that they can be neglected? Is that the good interpretation?
They're not neglected, they're summed, right? So you sum across the row onto the diagonal this way. And I mean, it does reduce the accuracy of the simulation somewhat, but not by much. But the error convergence rate is maintained, and then you can make up by just using a slightly finer resolution, and then a net gain is made. But my understanding is that this is tricky to do for tets and triangles. So we are using a hex mesh here, and then it's kind of straightforward.
Okay, that's it for me on paper 1.
Okay.
So over to Jonas and Peter.
Yeah. Peter, should you start or should I continue?
Well, if you have something, go ahead, please.
Yep. Okay. Yes. So I have my first question will be a very general question.
Okay.
On the first word. What is this?
Wave-based.
Wave-based.
Yeah.
Yes. So the methods you're using, are they based on waves?
They certainly model the wave phenomena.
Yes.
But one could argue that the basis is not a wave function.
No.
It's a polynomial, right?
Yes.
And indeed, I mean, there is, for example, this method, which is generally called the wave-based method,
yes,
which uses a wave type of basis. The reason why I chose this terminology is because this is the standard terminology in the room acoustics community to call these numerical discretization approaches the wave-based method.
So I don't agree on that either.
Right. Yeah, I know. We've talked about this before.
Yeah. So it is very important in scientific communication to use a good vocabulary.
Absolutely.
So that is not confusing.
Yeah. So I made, as you know, I made a comment about this in the thesis, at least. And perhaps numerical methods would be more accurate than.
You could argue about what word you should use.
Yeah.
But it's, I mean, some of the in the category that you're calling wave-based methods, the methods you're using are not based on waves, but there are other methods that are based on waves.
Yeah.
And in the other category, there are methods based on waves.
Yes. Yes. What I would find, you know, potentially confusing would be to call it something else than what it is generally called, you know, in case people were in the community were trying to read or figure out what this is about, then I guess most people in the community, when they read the title, they understand.
I don't agree on that.
Okay,
either.
okay.
So this is something that's happened quite late.
Yeah.
And in numerical acoustics, you wouldn't call the methods they're using there wave-based methods.
No, it's it seems to be restricted to the room acoustic community. Yeah. This term.
So I would like that all of us agreed to not use this term anymore.
Yeah.
Because this is very confusing and misleading.
Yeah. But then we have to go on a crusade throughout the community to kind of change.
I think the best way is to stop using it.
Yeah, yeah. I mean, I completely get your point. I completely agree with that this is a misleading terminology.
Yeah. Let's see. Now I try to find this again. So now it's more details.
Yeah.
But I think in paper 1, but also in some of the other papers, you're using point excitation, or you're excited with a Gaussian.
Yeah, so it's a distribution, pressure distribution.
Yeah.
It's not in one point, but.
So I have some problems getting. Do you have? Is it described in paper 1 or is it somewhere else?
It's certainly somewhere. Let me see. Maybe in paper 1 I only say it's a Gaussian pulse, but I think perhaps in paper 3 I have the expression. Here,
yeah, exactly.
This one.
Yeah. So what I don't get here is, so you describe this now in as a spatial distribution in space, and then at time 0.
Yeah.
So what happens? So this in time, this is basically. Should we think of it as a Kronecker delta, or should we think of it as a initial condition? Or
it's an initial condition. It's a pressure distribution, right? You know, if we think in 1D, it looks like this here. And then when you let it go, a pulse starts propagating that does not have a flat spectrum like a.
So how do you determine the spectrum of this?
You can analytically derive the spectrum of this pulse, the pulse that results from letting go of this initial condition.
Okay.
Yeah.
So that's the details I don't really get.
Okay. So yeah, I mean there is this fairly straightforward expression. The spectrum looks something like this. Yeah.
So is it but it's not determined. So it's totally physical. So it hasn't anything to do with the sampling frequency, or
no. But then and there's no forcing as such. I don't solve the forced system. I solve the unforced system with an initial condition.
Yeah. So it's just an initial condition in the
pressure. Yeah.
And it's not. Yeah. And the spatial width of it.
Yeah.
Is that influencing
the frequency content? Yeah.
Okay.
So the narrower the pulse in space. So a more rigorous approach would be to implement a forcing function, right? Then you can select, and you both have kind of a spatial distribution of the source and the time signal that you feed through.
So that's then the next step. So how, I mean, and you mentioned this in some places that, I mean, how to, because this, in room acoustics, we typically need source with a certain directivity or certain properties. So how would you go from this excitation to a more realistic one, or one that is useful for?
Right. I think, I mean, it depends on what you want to do. If you just want to estimate, for example, the reverberation time of a room, then this is actually pretty good. It's a uniformly distributing source. And you can, it's just assessing the relative energy decay at different frequencies is called. If you want to do, if you, for example, directly want to do oralizations, good, right? Because it has some coloration, you can say. So then using a source function, you would use some time signal that has something much closer, you know, to a spectrum of this, it would be better. And then directive sources, it's not something we have really touched upon at all in the work, but there is certainly work, and I believe, for example, Martin and his colleagues have worked on something with directive sources. And you have a forcing function with some model, the spherical harmonics model that allows you to have directive sources, basically. But yeah, future work.
Yeah. And one thing with the SEM and this
Continuous color.
Continuous collecting.
Yeah.
So the difference is that the SEM is you have a global weak form and a global system.
Yeah.
And in the other one, it's local.
Indeed.
Then I guess that the problem is to get a continuous function between the system, between the elements. Or
in the discontinuous one, you mean? Yeah. So that's handled through the flux terms there.
Okay.
Yeah. And then you can have different types of fluxes, and they have some different properties.
And how are they determined? The
fluxes. Yeah. I mean, the precise details I don't have in the top of my mind, but it's at least very established methodology of how they're determined. Yeah, I would have to.
I found it quite difficult to see this in the papers.
Okay. So we, for example, in paper 5, we derived this upwind flux, and this derivation was actually done by my colleagues Andersen and me of the upwind flux. It's somewhere here. The central flux is more straightforward. That's the one I used, for example, when I implemented the extended reaction foundation in TGFM. Yeah. But yeah, I would have to revisit the mathematics a little bit to give you a very precise answer on how they're derived. I must admit.
And the final question on this part, and that's the paper 1 again. On, I think it's in figure 2.
Figure 2.
That Martin also was talking a little bit about.
Yeah, the convergence plots.
Yeah, exactly. So here it's the element side that you have as the variable on the on the x-axis.
Yeah.
But so for this, if you keep the element size fixed, and then adding higher order polynomials. Are we then adding more
degrees of freedom in each element? Yes, which is not shown in this plot. So it doesn't tell the whole story. If you just look at this and you think, wow, obviously higher is much better. But there are these caveats, right? You add more degrees of freedom.
So if we would change the x-axis here to be the inverse of the spacing.
Yeah, you still see. I did some plots like that actually. That, in some sense, could be argued as more descriptive of the true benefits, right? But this is kind of the standard way of plotting error convergence. But this plot here tries to take this into account. So here we take into account both the smaller time step and the added degrees of freedom. And we still see it is a simplified measure, so it doesn't take into account all details of parallel computing and all that. But we see that the computational work effort is reduced when we go to higher.
Yep, that was my question for this part.
Okay.
So Peter.
Okay, I hope you can all hear me, and I want to start by saying thank you to DTU, with the DTU Acoustics Labs, for inviting me to this committee. I wish I could have been there. It's always nice to visit DTU and PhD defenses. Thank you also, Finnur, for a nice presentation and very impressive PhD work. It's yeah, it's a lot of work, as Martin mentioned, and I appreciate that you have taken on the FEM method, because as you mentioned somewhere, FEM has been around for a long time, but maybe curiously little has been done in room acoustics, whereas a method like FDTD seems to have been studied quite much more. And when you start to look at the equations, I can understand if you make your choice for FDTD, it seems at first glance to be easier, certainly. And we'll come back to FDTD a little bit later. As Martin mentioned, it is a very good initiative to team up with expertise in math and computation, as well as industry. So now it's fine to know that now we have a state of the art, a state of the FEM art that probably always will be referred to when authors list the various models. This will always be the studies on FEM together with Martin Hornix, as it happens. One little point about this terminology. Maybe if you, as you said, Finnur, we need to go on a crusade in the room acoustics community, but not to how to say, not to be too pessimistic. But the room acoustic community seems to be quite stubborn, because you all know that we use the term absorption coefficient for the boundary conditions. And also ISO standards in room acoustics specify that it should be called absorption coefficients. But maybe you also know that the ISO general standards specify that what we call absorption coefficient should absolutely not be called a coefficient. It should be called a factor. It should be called an absorption factor according to ISO itself. But the stubborn room acoustic community doesn't listen. So we'll see how that goes.
Right.
Then one little general thing. We will come back to more general aspects later, but it is very nice to see a time domain calculation method. But on page 9 in your thesis, you argue for time domain calculations. You write that simulating in the time domain is attractive because it offers a single pass broadband simulation. It allows for the visualization of the sound field and transient analysis, and it directly generates an impulse response that can be used for oralization purposes. And that is certainly true, but there's absolutely nothing that stops us from using a frequency domain calculation method and reach exactly the same impulse response and transient time signal result. If we have a linear time invariant system, we can choose one or the other path. So I think that those arguments are not necessarily telling why it's advantageous to use the time domain method. Because, you know, if I ask you to do a time convolution of two time signals, would you choose to do that in the time domain or in the frequency domain?
In the frequency domain.
Yes, but your end result is a time signal.
Indeed.
But having said that, the time domain formulation is perhaps or probably more efficient for this specific problem, anyways.
Yeah, I think this is a very, very good comment, and actually something I've thought about quite a lot. Because just to be perfectly honest, we just kind of started in the time domain when we started the PhD project, and it wasn't really a thought out decision. Should we do frequency domain or time domain? Just seemed everyone is doing time, or at least, you know, as you mentioned, the finite difference method is typically formulated in the time domain. So we tried to do this in the time domain. But I think there are strong arguments for doing it in the frequency domain too. And actually, we started the PhD project in Henning Larsen, in DTU, with the aim of almost, or at least one of the big parts of that study, that's my colleague Hermes, is in fact investigating a frequency domain implementation. And then we want to compare which one is actually better.
And as you point out, as one of the other groups working on the finite element method in room acoustics, there's a group in Japan with Okusono and Professor Otsuru. They seem to work on the frequency domain solutions, if I remember correctly, but you could maybe...
They seem to have done both, actually. So they also have some time domain. And actually more of the recent work, well, yeah, they do both. So yeah.
Okay, but then let's see some specific questions on paper 1.
Yeah.
You show this this way to handle the boundary conditions, and you use these terms of having so-called accumulator functions, and it seems to somehow be related to the time domain convolution of impulse responses that describe the wall behavior or the boundary condition.
Yeah.
You show some result diagrams where you can show that by using a number of poles to model the frequency dependence, it seems like you get excellent agreement. But I'm a little bit curious. It would have been quite nice to see the time domain behavior, so the impulse response of such modeling, because it can happen that we find some frequency domain expression that works perfectly fine to use in the frequency domain. But if we want to convert it to a time domain signal, then we have to make sure that it behaves well down to DC and up to half the sampling frequency. And we just have to assume that that is the case. And can you tell if you have seen any kind of material models that have caused such problems, or has it been completely unproblematic?
It has been very robust, I would say. And we have simulated several different configurations of materials, and it seems to work very well in all cases. So I haven't experienced this problem that you mentioned. Yeah.
Okay, that is certainly fine then.
And this technique, the auxiliary differential equation, it's also been called different things, but I originally came to learn about it from a book about electromagnetics, finite difference simulations in electromagnetics, a book from the 1990s, and so I think it's been around for quite a while. Yeah.
But maybe if it doesn't behave well for very low frequencies and very, very high frequencies, that is maybe, if there are any problems, they will perhaps be suppressed by the fact that you always seem to use a band limited source.
True. Yeah.
Signal.
Yeah. Indeed. So we will rarely go close to the half the sampling frequency because of dispersion, and yeah, we don't want to go below 20 hertz because we can't hear below 20 hertz. So yeah.
Okay. Then let's see. There's a figure, page 3305, figure number 4 in your paper 1.
No. Yes, this one. Yeah.
Yeah, I think that the information in this graph is partly has partly disappeared, and that is the fact that these curves do not seem to be parallel. But it's a little bit difficult to see. But I guess you claim that, or point out that the advantage with a higher order methods will increase as the number of time steps continue.
Yeah, that's it. Yes, and this is the general understanding that the benefits of high order, they become greater the longer you want to simulate, the more accurate you want to be, and the bigger your problem is. So kind of those three things.
Yeah, but it's and that fact is shown in the fact that the curves are not parallel, I think, and I can see that the blue curve doesn't seem to be parallel to the others, but for the other curves, it's difficult to see if there is any such phenomenon.
Yeah, so perhaps it's not a big difference, but I should emphasize that this is a simplified. It doesn't take into account all details. This it's a simplified model, and for a particular error tolerance. Maybe if we had lower error, we would have slightly different curves.
Yeah. And it's a long time since I saw a diagram with 10 to the power 15 range on the y-axis.
Yeah.
You specify for this that this shows the computational cost with a 2% numerical accuracy. And what does that mean? Does that mean that the error is somehow 2% at each time step, or at the number of wave periods?
Yes.
Is it the accumulated error up to that number of time steps, or is it the error at that time step?
It's the accumulated error at the final time step.
So you first make a calculation up to 1,000 time steps, calculate the error, then you repeat the calculation up to 5,000.
Yeah.
Okay. And this is for propagating a 3D wave. So that is in a case where we don't have any attenuation. So
indeed, it's just a free field propagation, so to speak.
Yeah. And actually, I had one more question related to what Jonas asked, but maybe it's actually not in this paper, the source, the type of source, point source simulation that you have used with this spatial distribution.
Right.
But maybe we can, I can mention it anyways, because this spatial distribution of a localized source, it leads to a spherical wave, and you say it has an analytical solution for what the time domain signal will look like.
Yeah.
So then, if we look at such a wave at a little distance from this source region,
yeah,
could we have generated exactly the same with a point source, which is difficult to implement in element methods, but a point source with the same time domain signal as results from your spatially distributed?
I believe so, yes. And I think doing something like that, well, like you say, implementing a point source, which is just in one point in space, is challenging, but you can have some small spatial distribution, which is the excitation point, so to speak, and then have a forcing function emitted from there, and then you have more freedom to select what type of time signal you get. Including, and you could including getting this signal out, yeah.
So if you would happen to have a very good omnidirectional source to use in your measurements, you have no problem to model that quite accurately with your distributed sound source.
I think so, yeah, yeah.
Okay. Then let's see. Then I think that the one case that appears in two papers, I think, is this case of 2D circular domain, figure number 5, and then the results in figure 6 and 7.
Right.
And I think that you are not completely fair to the straight-sided elements. You are not treating them as well as you could. So the results in figure 7, I think could be made much better, because it seems like when you make straight-sided elements, you always get the total area, which is slightly smaller than the circle, but the curvilinear elements get the right area. So if I would have done this, I would have scaled the straight-sided element model slightly outwards to get a slightly bigger radius, so that the total area would be maintained or would be correct. Then I believe that the resonance frequencies would be moving slightly towards lower frequencies. And the question is, do you have any idea if that would reduce the errors significantly, or that we still would see such a large difference?
That's a good question. Yeah, so you mean you would expand the size of the circle a little bit with the straight-sided elements to better, yeah.
Yeah, because you could do that to get exactly the right total area.
Right. Yeah, I don't have a good feeling for how the sort of the magnitude of doing that, how big of a difference that makes. Yeah, but you're right. I mean, maybe it's not entirely fair. Although one could say that, I mean, when you use a mesh generator to mesh, when you would go to more realistic cases, couldn't really do that, right? Those kind of tricks. You would have to just mesh with, you know, like we've done here.
Well, it depends on what the mesh generator does. We will have to talk to the mesh generator people to do it.
Yeah, yeah.
That's right.
Yeah, it's certainly not a theoretical impossibility to do it. Yeah, you're right. Yeah.
And the average error between the surface discretization and the wanted surface would decrease if we do it like that.
Mm-hmm, mm-hmm. Yeah, I didn't think about that. But yeah.
But now with all the time that you will have after your PhD, you can make such little studies.
Indeed.
So let's see. The last thing in paper 1 is that you studied a 3D room with frequency-dependent boundary conditions.
Uh-huh.
And you show results in figure 14, but there you don't have any reference solution.
True.
That would have been, it would have been very nice to see a reference solution.
Yeah, indeed. Is so. Does there exist an analytic solution for that case?
Well, yeah, for the single surface, plane surface, you use the solution by Thomasson.
Yeah.
And you are how to say, you are lucky enough to simulate just a single surface in a cube-shaped room to be absorbent. So you should be able to use the Thomasson solution with an image source cloud as sources, illuminating, so to say, or irradiating this entire infinite surface and get an analytic reference solution. And that would be very useful to compare with your detailed calculation.
Yeah, yeah. It's I did give it some thought, and I, for example, found an analytic solution to a cube domain with frequency independent boundaries. But yeah, I didn't think about this approach you just described. And you're perfectly right. I mean, this graph, you know, it's nice to look at, and you can see some frequency dependent behavior and so on. But it's very hard to assess whether it's actually the correct behavior or not. So yeah, it's definitely a fair criticism. Yeah.
Yeah. Okay, but then I think we are done with paper 1, and we agreed that I could then take the first questions on the next paper, which is paper 5, still of study 1.
Yeah.
And there we also have this cylinder case, but I will not comment on that. But it's I must admit that I cannot say too much about these implementations on parallel computing. It's very impressive to see that. I suspect that you have chosen a very effective way or efficient way to reach that by using existing tools and experts on this. But let's see. I did notice that you used a number of different error measures here. That's not real important. Most types of error measures are quite strongly correlated, but you use the infinite norm, so the maximum error in one place. You use what looks like error norm 1 in another place, and then the relative error for a third version of epsilon. But I guess maybe that was just as it happened, perhaps, or you haven't.
Yeah.
So yeah, there you see one with the infinite norm, which would be the maximum error.
Yeah.
And then on page 8, just above figure 5.
This one?
Yeah.
No, so yeah. Is this figure 5 here? Yeah, yeah.
And then equation 36, then you have a relative error.
Right. Well, this is slightly different. This is not an error of the simulation as such, but an error in the fitting. So I thought it made a bit more sense to use this measure here to give a more a more intuitive number or something that's but this is an error measure I came up with myself, and it's open for criticism, let's say. It's a way to measure the mapping accuracy, but certainly not, or there was almost certainly other ways to do it as well.
Yeah.
But for this, but comparing this one versus this one, maybe this is a typo. It should be infinity here. I think this could be a typo, but I would have to double check that. But
yeah. But anyways, we always want the errors to be small, and we understand that when errors go smaller in a diagram, that's a good good direction.
Yeah.
Even though when we talk about the value of an error, to understand the meaning of that value is a little bit important to know what type of error it is.
Yeah.
Now let's see, what's here that you discussed that just below figure 5 on page 8. You go down a little bit. You discussed that the error plateaus at around 10 to the power of -7, which is likely due to aliasing errors that stem from the transformation Jacobians and normals no longer being constant. That is for the curvilinear elements.
Indeed.
And is that because the transformation that you do, it is an approximation so that you can use your prototype elements for doing the integrals? Or
yes.
is it so that you could, in principle, calculate the integrals exactly also for the curvilinear elements?
As I've understood it, it is the former approach you described. So we do not precisely compute those integrals when we have those non-constant Jacobians.
Okay. And
but this was, to be perfectly honest, this was a bit of a mystery to us, and is still. So could be interesting to investigate this further. Why we can't go below 10 to the power of -7.
Yeah. And in your case, when you study a symmetrical case like the cylinder, isn't it so that you could afford to calculate the integrals exactly if you have many, or more accurately, if you have many identical elements? Or is that actually not the case if you don't have an asymmetrical excitation?
Yeah, I'm not sure, to be honest. I would have to think that over. Yeah, I don't have a good answer to that, I'm afraid.
Okay.
Yeah.
More things on the to-do list that you...
Yeah.
For the life after.
Yeah. You can probably spend a lifetime on this and still things could be improved further, you know.
But a good research study should maybe answer one question and start to generate two new.
All right. Yeah. This whole project has certainly done that for me.
Yeah. Let's see, but the results very often look very impressive. In figure 7, when you show the simulation of a single reflection from a surface, it's a little bit difficult to see, but the match for the magnitude seems to be really, really good. And is it equally good for the phase, or is it a little bit difficult to separate the curves? But is it as, maybe it is actually as...
It is very, very spot on, but it's hard to see. It is perhaps here, it's hard to say whether this is a perfect match or, but it is a very good match indeed.
It is an agreement that almost makes you want to cry of happiness when you see your simulation results match that well.
Yeah, indeed.
Then it's impossible to start to look at what you can do, how large problems you can study. And that leads to a question about this method versus the FDTD, because if I understand the results in table 13 on page 13, you have studied a huge concert hall which has a volume of 20,000 cubic meters.
Mm-hmm.
You seem to get the results that you trust up to 1 kilohertz. If you use a configuration with 4 GPUs, it takes something like 6 hours to calculate a 2-second long impulse response.
Yeah.
That seems to correspond to approximately 10 to the power of 8 points, I think, in 3D. I don't know if that is, if I've calculated that correctly. We could also say that you make a calculation up to KL around 27,000.
Yeah.
Well, no, not KL. I took the frequency times a one-dimensional length scale, because that tells us how large a problem is somehow.
Yeah.
Then if we compare with FDTD, Stefan Bilbao's group in Edinburgh and Brian Hamilton, they published a paper a conference paper in 2016, where they showed results for a concert hall of 12,000 cubic meters. They claimed with a sampling frequency of 26 kilohertz that they trusted their results up to 4 kilohertz.
Mm-hmm.
And to calculate a 2-second long impulse response on the configuration of 2016 with 4 GPUs took them 70 minutes. And that was for a KL of 90,000, so 3 times as high as your.
Yeah.
In shorter time, much shorter time.
Yeah.
4 years ago.
Yeah.
So do you have any comment?
I have several. First of all, I think we should, a general comment is that head-to-head comparisons of different simulation techniques and methods, algorithms, implementations, they are hard. It's hard to do apples to apples comparison. You're typically often doing an apples to oranges comparison.
Yeah.
Because there are so many design choices involved, so many implementation details and so on, and hardware and all that also too.
Yeah. It is a cheap point or a kind of simplified question, but it's I think it's a relevant question.
Yeah, but yeah, absolutely. And FDTD is probably hard to beat when it comes to geometries that neatly fit to a Cartesian grid. When you have a high order FDTD, the parallel efficiency can be very high, and as I say, it's hard to beat. So for an empty shoebox-sized rooms, I would assume that their approach is faster than ours. But as soon as you have some complex geometries, and actually Bilbao and co-authors have done a study on this in 2016 paper, where they show very neatly the importance of having an element-based method where you can capture the complex geometries, because if you have a regular grid like an FDTD, then you never, when you have a curved surface, you never converge to the true surface area of the geometry, even in the limit of a very fine mesh. And that yields very large errors, especially in time domain parameters like reoperation time. We pay a price for the added geometric flexibility of DGFM, but in terms of efficiency, but we gain in accuracy. And then the second thing is that I looked at those results in that paper, and the conference paper you're referring to, and we are not talking about the same level of accuracy. So I think in general we have to be very precise what level of accuracy we're talking about, and the discretization that they're using there is lower than what we are using here. So what they say is good up to 4K is not equivalent to what we say is good up to 1K.
I completely agree that one has to be very careful there, because with the scale factors that we see with these methods, that one design choice or one choosing a certain error as a goal can affect your calculation time dramatically. Even though we have to acknowledge that they have developed methods to handle the curved geometries by having a layer of flexible elements.
Absolutely, and their approach is very interesting, and it could well be that it is faster than this. I'm not excluding that option and capturing the same level of accuracy, but it's hard to do head to head. And I would maybe also say at least their approach is at least hard to extend to high order accuracy. In general, finite volumes is hard to extend to high order accuracy in 2 and 3Ds. And when we want to be accurate, when we want to simulate large domains and so on, the high order accuracy is very helpful. And and I think, you know, these techniques that are presented in this study, in this project, they are, I think we can argue, the most advanced, or some of the most advanced numerical techniques available now. And you see the trend in different fields, and see it in computational fluid dynamics, electromagnetics, and so on. They seem to be moving towards these methods, and I think that's for good reason. So I have confidence in our approach, you know, that it's at least can compete with what they've done.
Yeah, it's great to have more horses in the race.
Yeah, right.
Okay, I think I'm fine now with questions on the study one, and then I think it's Martin and Jonas to take the word.
Okay, I'll then decrease the volume here.
Okay, I only have one question to paper 5. I think otherwise we calculated that we are done by 4 p.m. if we continue in this pace. That is on the baseline, because it seems that you use the GPU. You use the GPU 1 as a baseline, huh? So, I mean, you don't compare with only CPUs. Is that because it's not feasible anyway to do that?
We did actually compare against CPUs, but we ended up taking it out of the paper because it was somewhat of a straw man. So actually we saw going from one CPU core to several CPU cores, and we got very nice scaling. Like if we went to 16 cores, then we got a speed up of 15 point something. But then going compared to that, then adding one GPU, we saw a speed up of something like 1500 or something.
Yeah.
But that's not a fair comparison because the CPU implementation in LibParanormal is not optimized at all. So this is why we removed it.
Okay. And if you go to figure 8, you show the
8, sorry. Where are we?
Yeah,
this one.
Yeah, the speed up compared to 2 GPU baseline.
Yeah.
But what happens with the CPUs? So do you keep the number of CPUs equal among those cases, or does it also increase?
It also increases.
Okay, good.
So you have this, where is it? It's illustrated quite nicely here. So for each GPU, you have a CPU kind of.
Thank you. Yeah, that was my question on paper 5.
Okay.
Jonas?
Yeah. So I think we should continue to study 2.
Yeah, sounds good.
Let's see. Yeah, and that's then about the how to model the boundary conditions and uncertainty and so on.
Yeah.
So I have some questions on paper 3.
Yeah.
So let's see. So so here you're not using the numerical acoustics methods. So you're using geometrical acoustic methods.
Indeed. The inspiration came from Harrison, for example. Yeah. How do they do extended reaction there? They detect, or they know the input, and they choose the relevant shortcoming, depending on it. So yeah, it's
yeah. Yes. And then you're using Thomason here now. Let's see.
As the analytic solution.
Yes, exactly. Yeah, and you get very good results. But I was a little bit surprised that you were using Thomason without at least explaining how you're doing this.
Okay.
Because in Thomason's paper on this is Thomasson's paper on the reflection in a impedance boundary.
Yeah.
And the case he is looking at is local reaction.
Yeah. Yeah.
But your point here is that you should have an angle dependent.
Yeah.
So how you
yeah.
doing this?
So the way we did this is that we know from material models or the transfer matrix model and Mickey's model combined that we know the incidence, the angle dependent surface impedance as a function of angle, right? Mm-hmm. And then in the Thomas's model, we simply use the impedance for the right, for the angle. So if the incidence angle like here is 65 degrees, then we select the 65 degree angle and compute with Thomason's. Use that as the boundary condition in Thomason's model.
That's not really Thomasson's model.
Okay. Okay. Yeah.
So you have been inspired by Thomasson's model and then done something with it.
Okay. Yeah.
And it's Thomasson's model is and this is based on some old papers from going long back.
Okay.
And then he has to do a small mathematical trick to get an expression that is numerically easy to compute.
Right. Yeah.
But it's based on local reaction.
Yeah.
And I guess that the basic, if you go to the basic equations, you can actually just shift the admittance in that case and do the numerical integration.
Okay. Yeah.
But the point of this is that the point in his paper is not to study extended but for the case he's studying, then it's an exact solution.
Yeah.
You're doing something else.
Yeah. Yes.
Yeah. So but it's probably a quite good approximation.
Yeah, I think so too. Yeah, but perhaps not.
But it's not described in the paper.
Yeah, it's a good point. I mean, yeah. So I think I write just. Well, I don't remember. Yeah, but yeah. It's a very good point. Something we didn't really think too much about. We just did it. Kind of.
And then you're detecting the direction of the waves.
Yeah.
In a quite clever way. So you're taking some points upwards, and then as you also have, if you just have the pressure, then there is no direction in a point, but you also have the velocity.
Yeah, exactly.
And then you separate the direction of two.
Yeah. So actually, I only do the wave splitting on the velocity components.
Yeah, exactly.
Yeah.
But you have the problem is that you have when we have grazing incidents, you will have
absolutely. Yeah. This is reflected in the error here, right? Yeah. This one here.
Yeah.
So it works very well for low incidence angles, but for higher, we have higher errors. And
so if you think of alternatives of doing this, now I'm just thinking when I was reading the paper, but you have the points on the surface. So could you think of another way of doing this?
Yeah, I can think of one way, which I tried, spent some time on, and in the end it didn't really work so well. So maybe I shouldn't go too much. But the way if I go here, if I have the 3 points here, and the wave is coming in here, then what I tried was I detect the angle in the normal way, and let's say the true angle is 45, and this approach says it's 40. Mm-hmm. Then I do an iteration, and I shift these nodes to go to 40. That's my best estimate, right? And then I do it again. And then then this is kind of almost normal incidence to this, and I should get a good estimate. But it didn't really work. So that was.
So I was thinking on something much more simple and straightforward.
Yeah, okay.
Beamforming.
Yes. So some sort of, I'm not well versed in those things, but yes, I believe if you do some sort of more 2D, 3D distribution of points and do some smart signal processing.
Because you have all points already. So,
yeah, absolutely. That's and we mentioned this in the paper that this is somewhat of a, not just this normal way here. It's a limitation of the method, and it could certainly be improved.
Then you could argue that, or say that the biggest limitation of this method is that you need to have just one instant wave at a time.
Yes, absolutely. And
do you have any idea of how to get around that?
Domain coupling, the other approach we did.
Yeah, but that's, I mean, so if you want to avoid that and model it.
No, but I'm all ears if you have a good idea. We thought about it, but when you have many waves impinging at the same time, also, I mean, then you have to, you have the boundary, and you have some points in the boundary of the mesh. I have many waves coming in at the same time. I can only select one boundary condition here. So even if I could detect some advanced direction of arrival things to detect 3 incidence angles at the same time, I couldn't really use that information because I can only select one boundary condition.
Yes, but you're thinking of the surface as described in one point at a time.
Yeah.
But you have a surface, and if you consider the entire surface as one material.
Yeah.
And now, perhaps because you're doing this in time domain, and I'm probably thinking in frequency domain.
Okay.
But you could have done a spatial wave transform on the surface, and then from that get the wave number spectrum, and that corresponds to the incident angles. But there's probably, I mean, now it's just you need to.
Yeah.
You need to. There's probably a lot of.
Yeah, exactly. That's a big thing to.
It's easy to think of or talk about. Other ways to do things.
Yeah, that could be interesting.
Yep, that's my question.
Yeah.
I can continue there.
Yeah.
And one of the problems you will get is aliasing. But I had actually another suggestion how you could do it, making use of the fluxes in DG. Because if you have upwind flux, then what you do is you calculate the outward going part of the wave normal to the boundary.
Yeah.
And you make use of the pressure and velocity. And you can calculate the incoming angle from that.
Right. Yeah. Yeah.
We can discuss it later.
Yeah. But yeah.
Because still, I think you still have the problem that is only for one wave. Then
exactly. So
unless you include more a larger part of the boundary, but it only works if you have a boundary of one material. So if you have small materials over here and there, it's harder. Let's see. I had another question here. Do you do something with frequency dependency on this angle calculation, or do you have one angle for all frequencies?
One angle for all frequencies.
Okay.
That could yet another thing that could be looked into is to do it at different frequencies.
Yeah. And you compare with results from an experiment.
Yeah.
Does the experiment do you exclude the boundary effects, the edge effects from the measured results? No. Okay.
So those fluctuations in the measured data, I think the edge diffraction is the biggest cost there. Yeah.
And you show that you have 3 points in this small FDTD approach. Did you try with more points?
Yes.
Yeah. Didn't help.
Or we did a fourth order FDTD or FD calculation.
Let's see if I have more. Yes, I also had the comment on that method from Thomas, and I think there's other approaches that give a better and can include extended reaction. And we could help if the paper is still can be modified. I don't know.
Yeah. It's actually been accepted, so I can't make
Congratulations.
But maybe for the other one, the domain coupling one, where I'm using the same approach.
Otherwise, I only have minor questions here.
Okay.
Peter, up to you. Otherwise, I think we can go to the next paper in the study.
Okay.
So, Peter?
Could I throw in? I think maybe two small questions. The first one was what you just discussed. Oh, sorry, I should turn on my video. So what you just discussed, you Finnur, you confirmed that in the measured results you had not excluded this edge diffraction effect, but I think in another paper you pointed out that you stopped some simulation or measurement, I don't remember which, before the first arrival of.
That's in the simulation. That's in the simulation. Yeah. So then because we can't really do an infinitely large surface, we have to do a box, and then we stop before.
But then it would have been a more fair comparison if you had done the same with the simulation and the measurement, to truncate the measured and simulated impulse response at the same point in time.
Good point.
And maybe that would have given a better agreement, possibly.
Yeah.
A second question, if you look at figure 5 and 6.
5 and 6.
Or if we start with figure 5.
Yeah.
I would say that if we look at the extended reaction results, I would say that for the top graph, the difference between those two curves is very small. And then in the middle graph, I would say that the difference is clearly bigger. And in the lowest graph, that the difference is the largest of those three.
Yeah, you mean between the extended reaction and the analytic?
Yes.
Yeah.
But then if we look at figure 6, I don't quite get that impression when we look at the results for 65 degrees incidence angle, and we look at the red dot. Then I would say that for case A and B, the results seem to be the same, very similar, and even slightly larger for case A than for case B. If you look at the red, exactly.
Yeah.
And then it's somewhat bigger for case C.
Yeah.
So those two first ones don't agree with the impression I get from the top two diagrams.
Yeah. Yeah, it is a bit strange, this thing here, but at least I can say in general that this measure that we're showing here, it's it's the average, it's the mean error in all points across frequency. So it's not a very, to be honest, not maybe the best or most insightful way of looking at the behavior here.
But it is but I hope it's the mean of the absolute value of the deviation. So
that's at least what it should be, yes. But this it is indeed strange why this one is higher than this one, because that really can't be. Well, keep in mind that the axis here is down to -40, but this one is only down to -15. So maybe something that looks.
Oh yes, you're right.
Yeah. So maybe that explains it. So, and maybe this should have been plotted with the same axes, but then this would have gone out. Yeah. But yeah, that probably explains it.
Yes, it probably does. You're right. Okay, but then I don't have any more. Yes, actually, one more thing. If you would like to use this technique, how would you, if this technique could be useful for the first part of the time domain calculation, first part of the impulse response in a room, how would you make a transition to turning it off? Is that
yeah, so you could use, when you know the volume of the space and then the width of your initial condition, you could kind of compute circa how long you could use the method, and then you can switch to for example, a field incidence, so an ankle averaged boundary condition. And this is what we have done. We did some experiments actually with this, where we simply switch from one to the other, and that works fine. Okay,
even if it's always a bit tricky because you might encounter cases where such a switch will generate some audible effect.
Yeah. And I was concerned about that, but there was no, at least in the cases we looked at, there was no weird, it's such a fine time step, and then you just switch from one to the next. So maybe there's a small jump in the boundary condition right when you make the switch, but it doesn't seem to result in any noticeably weird behavior.
Okay. Okay, then I'm fine with this, and I think that we have one more paper from study 2, paper 4, and Martin could perhaps take the lead there.
Yeah, sure. I can start. Yeah, so paper 4 is, I would say, much more promising than the previous one, although it was a very good attempt. I think it was really worth it.
I agree.
And these results of this paper look very good.
Yeah,
it's really promising.
I agree.
You use in the first page, you write something on what set of equations you use to solve for the material, and you use an equivalent fluid model. So basically, a porous material is treated as a fluid.
Mm-hmm.
But you say that, okay, we simplify Biot's theory, which where there are 3 propagating waves: an elastic compression wave, an elastic shear wave, and an acoustic compression wave. To reduce the computational complexity, an equivalent fluid model can be used, but it both reduces the fact that you have a porous, it's a small pores, so it's like a bulk material.
Yeah.
Also, it's a rigid frame model now. So you don't consider that the material itself has elastic properties.
Yeah. Well, I think you can do, as far as I understand, I'm maybe not the biggest expert in porous materials, so compared to some people at least, but I think you can do a small correction, and then the frame can either be rigid or what's called limp. But this is still an equivalent fluid model, so you still just have the compressional wave. In general, I can make a comment maybe that, I mean, of course, it's possible to solve the full PO theory, but as far as I understand, you wouldn't gain much out of doing that, and of course, it adds some cost.
Regarding the fluxes at the interface between air and your porous material, I thought I read that you treated that from the air perspective as a locally reacting material. Is that true, or do you use central flux?
Central flux.
Okay.
Yeah. And DG is brilliant here, right? Because you're anyway solving all the elements discontinuously. So it was very straightforward to all of a sudden have different physics in one element compared to the other.
You wrote, I think you also mentioned it in your presentation, the speed of sound in porous materials is smaller, so we don't have this time stepping problem, I think.
Yeah.
But the elements also need to be smaller because the wavelengths are much smaller. So does that scale in the same direction, or?
Well, I mean,
so basically the question is the porous material determining the time step, or
yes. So in this, there's some room for improvement here compared to the way we do it. So I mean, if you have a room and it has a suspended ceiling, let's say something like this here, which is very thin, and then if you're only simulating up to 1 kilohertz or something, then maybe the air domain elements are like this. But then of course we need to have these small elements here to capture this geometry. And then the way we've done it is the time step is restricted.
Okay.
This element. So local time stepping is the solution here.
Okay. Can you show please figure 2 of this paper?
Figure 2, yeah.
And so these are the real and imaginary parts of the surface impedance, but the imaginary parts are mostly negative.
Yeah.
Is that true? Or is this the negative part of the imaginary?
Doesn't it depend on how you define things? You can. I'm not sure.
You mean what convention you use?
Yeah. Doesn't it depend on that? Yeah, I'm not sure. I mean, this is at least what I got.
Which time convention you use?
Minus j omega, I believe. As far as I remember.
This is also my approach to go through to look at it and go through the equation and look if it's correct. But
yeah.
Because most people use they plot this and then they write, okay, this is the negative part of the imaginary.
Okay, I see. Yeah.
So,
okay. Yeah. I know one other paper that was doing something along or similar to what we were doing here, and then their graphs looked like this one. But yeah.
Let's see. Yes, in section 6 of this paper, you have 3 geometry. They are still quite simple, huh?
Absolutely.
So, this means that, if you compare the results, then there's basically no scattering.
Yeah, absolutely.
And do you have a thought on how this would influence the results? Because you have T20, EDT, so this typical parameters that are influenced by scattering.
Absolutely. So I mean, we would get very different results, but whether the error magnitudes would be smaller, I'm not sure.
And then a question which maybe suits more the section on virtual acoustics. Yeah. So what I also like in your work is that you often compare with J&Ds, right? Because then you go to the perception and not only to the physics in comparison. But those J&Ds that we have in room acoustics are mostly for a receiver that is static. Yeah. And also monaural sounds. And you already have shown in your presentation that if you have to assess the location of a source, we are way better if we are allowed to rotate the head. And if it's a binaural signal. Yeah, indeed. So what do you think? Should we go to other J&Ds for?
For virtual acoustics, absolutely. Yeah. Absolutely.
So that means also that we should think different also if we compare.
So I think this comparison is kind of valid because it is for the static case, right? But in general, yes. I think you make a very good point then.
Yeah, but although I don't know if T20 is perceived differently, because I don't know what.
It's it could be interesting to investigate. But I mean, one very good example of this moving around thing, how that changes, is when you think about diffraction, right? Yeah. I mean, if you're in VR and you walk past the pillar, you don't have the diffraction modeling, then that's very clearly perceptible because the volume kind of jumps up and down. But if you're doing static scenarios, then you don't have this movement.
That's it for me. Peter?
Okay, let's see if I have anything left to ask here. About these last cases with comparison with measurements, the table 5 that we are looking at. Let's see, I have to start the video again so you can see me.
Table 5, you said?
No, table 5 in this paper we are looking.
Table. This one, sorry,
yeah. So this is the deviation from the EFM solution.
Indeed.
But do you have any data on the variation or uncertainty in the measurements? Because
there's no measurement involved here, right?
No, that's true. That's only for the single surface.
Yeah, right. But
But then how about the spatial variation in simulations? I don't know if you get a spatial variation in your simulations.
yeah. I mean, these results are averaged across the 3 receivers, so it would make sense to have some indicator of the spatial variance between the receivers here, which we haven't. And it's a great point. Yeah.
Because it is like if we think back to Forlander's first round robin paper, he showed the difference between simulations and measurements, and also showing the uncertainty in measurements done by a number of different groups. So in the same, it's a similar situation here, that what if the confidence interval, if you want to say so, of your simulations, if your reference simulations, the EFM, what if the confidence interval is larger than the difference between the different methods?
Right.
Then you cannot draw any conclusion based on that difference, I would say.
But you mean the confidence interval with respect to the position of the receivers?
Yes.
Yeah.
Because you say that you have 3 receivers, and if the spatial variation is large enough to give you maybe not 10%, 20% variation, but there will be some variation, and we have no idea what that variation is based on the results we see here.
Yeah, maybe I could simply present the detailed results here. Yeah, or at least some indicator. Yeah.
Okay, but actually, I don't have any more results, except that it's perhaps a little bit frustrating to go from looking at the method with accuracies or errors of 10 to the power of -6, and then you have to live with, when you compare with real measurements, and you have to try to explain or accept differences of 3 decibels or more.
Yeah.
How do you handle that?
I think, certainly there are the measurements, there are imperfections in the measurements, so we should not take them as the perfect ground truth. And I think I'm confident in saying that that the improvement is clear, even when we compare against the measurements, but certainly when we compare against the analytic solution, that there is a benefit in accuracy here. But how accurate do we have to be, and how much important are the numerical, these very low errors that you just mentioned, compared to these coarse errors in the input data and so on.
Or not errors, but uncertainties.
Yeah, uncertainties. Sorry, yeah.
Because measurements, we could claim that the measurements are the truth.
They are the truth for the system that was used, the model that was used, the setup that was used, etc.
Yeah, and it's we are still a few decibels away from that in many cases.
Yeah, that's true.
Okay, but then should we take a quick look at the paper 6, which is also a part of study 2, and I can continue. First, one thing which is not immediately related to the study and the error analysis is, if we look at figure 5 and 6.
It's coming up here. 5 and 6. Yeah,
so here we actually get quite a satisfying agreement, I think, between measurement and simulation.
Yeah.
In a room. And what comes to mind is that there was a study by Mike Arret in Acoustica some years ago. I think he studied similar things partly similar things in his PhD thesis with Michael Forlander. And he showed that in the scale model box, when they used rigid walls or hard surfaces, they got excellent agreement between FEM calculations and measurements. But as soon as they switched to using some kind of porous material on 3 of the walls, if I remember correctly, the agreement was frankly very much worse.
Yeah.
But this looks clearly much more convincing.
Okay, yeah. I think, I agree. I mean, I think these results look pretty good, but I think also it's we have to be a bit careful when we look only at the results in the frequency domain, because in the eyeball norm, when we look at these graphs, they look pretty good, but actually the reverberation times might not be so great here in all the octave bands. So, and I think, you know, personally, it's maybe a bit something I've noticed, that it's very common when we talk about wave-based methods to compare frequency responses for transfer functions. But
yeah, but I would argue I would not be more convinced if we have to start with an even worse frequency response.
No,
I would not expect that to behave better in the time domain than these results.
No, of course not.
So this is kind of necessary but not sufficient.
Yeah, exactly. Test. And we did struggle, as we see when we propagate the uncertainty through the model, that the time domain results, they vary significantly, right? And we had a hard time sort of simulating this room with enough accuracy when we look at the time domain results.
Yeah. Also, this paper is about about using this special error analysis framework. But then it's, and you have decided to look at the time domain parameters, T30, etc. But then it becomes a little bit of a contrast when if you go back to figure 5 and look at, if we look at the text above figure 5, it says, by visual inspection, a good agreement between measurements and simulations is observed. That is a slightly different, how to say, approach than the very careful error analysis of the time domain results.
Yeah,
because we could have done the same here, I guess. Some kind of more careful or more quantified analysis.
Yeah. Yes. So one thing we struggled a bit with, we thought about that, and is for this framework you kind of need some, or at least I believe you need some sort of a single quantity measure. So you need to measure, which is very convenient when you have a reverberation time. It's just a single number. But when you have a function here, then you know, you need a single value that describes the agreement between simulation and measurements here, and it's it's hard to get a good measure of that in a single number. So this is why we didn't in the end do any of the frequency responses, any uncertainty quantification of those, because if you, for example, do the shape similarity measure, you know, it's just 99.9% or 99.5% for all cases, kind of. So yeah.
Yeah, but certainly you have in other papers you specify or you looked at the average deviation in decibels.
Yes, we did, yeah.
But that is also very vulnerable to, for instance, dips that are misplaced a little bit.
Exactly. So it's tricky. At least the time domain parameters are very straightforward to use in this framework.
Yeah, but I actually don't have any more question here except acknowledging that we cannot escape from this fact that we just talked about previously, that there's a large uncertainty. It's almost the elephant in the room, the uncertainty when we look at a real world case and try to set up a model for that.
Completely agree.
Yeah. But I'll leave the word to Martin then for this.
And on it goes, huh?
Yeah.
Many papers, many questions.
Yeah. We can also talk afterwards.
Yeah, sure. I'm also saying this to Peter and Eunice. I would really appreciate to have some time for the remaining ones. So some key questions there. So I limit my questions here.
Yeah.
Actually, you write on the flow resistivity you received for the two materials 5,875 kilopascal second per square meter.
But
the my experience with measuring flow resistivity of samples of one panel is that if you take some samples of the panel and measure, for every sample you find a different flow resistivity with a quite significant deviation.
Okay.
So this is a bit ambitious to claim, I would say, although it would be an average for Fenner. I don't know.
Right.
But that's also part of the uncertainty.
Yeah. So you would think that the deviation should be higher, essentially.
No, I would say it's hard to I'm sorry. Sorry for my question. I was just thinking that these would be the values of the materials. But my comment is more that the values you get from the material.
Yeah.
That from my experience, the materials inhomogeneous, even if
within a single panel. Yeah.
Absolutely. So just a side note. And then a more general comment on this paper is, again, what do you think the influence of scattering would be? Because also here, the space is quite
yet another empty rectangular room.
Which is a good departure point. And it's also a paper where you introduce a methodology. So I think it's...
Yeah, I mean... somehow I think when you have more scattering, it becomes easier or less sensitive. You know? Sound feels more diffuse, and so maybe less prominent differences between simulations and measurements and so on. So we're not, and actually I think, I mean, when we picked the room, it was partially because this is a room that we have access to, but we thought this is a super simple room. It's a good ground case to work from, but then we find that it's actually a very difficult room. A rigid rectangular box is a very difficult room to simulate accurately.
Jonas.
I have nothing more here.
Okay, then we move on.
Okay.
Study 3. That's paper 2. That's the VR paper. I would like to start with a question which is a bit similar to Jonas' wave-based question, but it's not. I don't have a position in this comment. You used interactive virtual acoustics, auditory virtual reality.
Interchangeably.
Well, no, I think there is no common ground on how we should call these approaches. So do you have a suggestion? Because it also relates to what components it includes. So in this work, you also show, audio only, audio visuals, transportation included. You can include movements.
So at least I think when we use the word virtual reality somewhere, then we have to have an immersive visual, right? But I mean, you could use this entire system exactly like we've proposed it, where you just have headphones and you sit by a computer, kind of like playing a first-person shooter game or something like that. Then it's maybe not auditory virtual reality, but interactive virtual acoustics, perhaps. I think interactive virtual acoustics is maybe a bit more general term for this thing of having some interactivity involved. And then also, I talk a bit about room acoustic simulations versus virtual acoustics. I think virtual acoustics is a more cool phrase.
Because, for example, interactive is that if you are allowed to rotate your head, is that interactive already?
Yeah, I think so. So somehow room acoustic simulations is the standard old-fashioned way, where you just have a single source receiver combination looking in one direction, you know.
Because we used auralization for a long time.
So the static auralization.
To name like listening to recordings or predict.
Just point out that there's now 15 minutes left.
Thank you.
Choose your question.
Now I choose my. I start the cherry picking of my questions. In this paper, you use a geometrical acoustics based method. But somewhere in your thesis, you write that geometrical acoustics methods in virtual acoustics are known to be less appropriate.
Yeah.
But still, you do the listening test with this system.
Yeah. Purely for practical reasons.
Yeah. So
kind of.
would you then say that the results are kind of a baseline here, and then you can say, okay, if you improve your prediction methods that you feed in the system, you can only improve, or do you see it in a different way?
I would hope so. Yes, exactly. Yeah. So yeah, I think that's a fair assumption.
Yeah. Then I have a question on the outcome of the angle localization.
Yeah.
That's I don't know what figure it is, but maybe you can show it. Yeah.
Yeah, here we go.
Yeah.
Yeah.
So with higher, the second order ambisonics performance is better. Is the difference also significant statistically?
Yeah.
Okay. Very good. I leave it to Peter now. I have many questions, but
yeah.
Move on.
Okay, I think that I don't have anything I want to bring up now, because I would also like to see that we have some time for rounding off discussion. So I think that we could move on to study 4, unless Jonas has something he would like to ask for this study.
Yes, so I do have some more questions, but I also think we need to move on. So,
but we can talk later also. I'm more than happy to talk.
So should we say something on study 4 then? Who will start?
Yeah, I could just have one little comment on paper 7, the first one of study 4, and this is purely about geometrical acoustics, and this is not your main work, but I think that in this work I lack a little bit of references to the beam tracing method, because I think that you use the 2 steps of calculation effort for the image source method, what you call the test of validity and the test of visibility. And I'm not completely convinced that your test of validity is reducing all the enormous number of image sources that you need to test if you are doing that in the most efficient way. So could you any comment on that, whether the beam tracing approach has been discussed here or not?
Well, yeah, a short comment is that we have not really taken that into consideration.
Because the beam tracing method, I think, is a superior method to reduce the number of valid image sources.
Okay. Yeah. So, yeah. Absolutely. That makes perfect sense. Yeah.
And that would I don't know if it would change the conclusions. It would reduce this image source tree that needs to be tested for visibility, but maybe the conclusions still would hold.
Right.
But, yeah. But in the same way as you have used the state-of-the-art techniques for your other part of your studies, I think that the beam tracing method would have been considered as a state-of-the-art for the image source method.
I see. Yeah. It makes perfect sense. That's a very good point.
Yeah.
And I would maybe just mention that this study is it's certainly not complete. It's a preliminary study. Yeah.
Oh. But then I'll leave the word to Martin if you had anything on the last paper, the paper 8.
I for sure I have questions there. I have one remark on paper 7.
Yeah.
Because I wonder the relevance of including many image sources in a solution, because often you combine image sources and ray tracing. So if you only use like up to a certain order, then
yeah. So it seems to be common to just go to order 2 or 3 or something with image sources.
Yeah, but not to 10 or.
Yeah, exactly. And we do, as far as I remember, most of the tests we do up to 3rd order.
Okay.
Yeah.
Good. Paper 8.
Yeah.
Which is was very interesting to read, because it's also something new for the acoustics community.
Yeah.
At least in this field.
Yeah, indeed.
So you have a reduced order method, and you have the full result of your room acoustic model, and then you go to reduced order basis.
Yeah.
It's a basis with basis functions that are orthogonal, so you actually project your results on that.
Yeah.
So as an acoustician, then you have some expectations of your curious on how those bases look like. So
Yeah.
have you looked at your basis functions, because they are spatial values, right?
Yeah. No. Unfortunately not.
Because in your, to be honest, when I was reading this and I saw your two-dimensional case, I was thinking, oh, but those basis functions, aren't those the modes of the space?
Yeah.
Because that's also like an orthogonal basis.
Yeah. Yeah. So that would be very interesting to look into.
So I would be really curious to see how the basis looks like.
Yeah.
Yeah.
So this is a draft of a paper, right? It's
Yeah, sure. Yeah.
work. So that's a very great comment that
Yeah.
we left into the finalized version. Yeah.
And because that could also help to understand, to link the physics to the
Right.
methods.
I mean, there are some numerical methods that use, like the wave-based method we talked about earlier, that uses kind of some smart or basis functions taking into account the physics.
Yeah.
And how this way of deducing the basis compares to those ways. I think it's going to be very interesting to compare.
You ran some calculations and a comparison up to 0.05 and 0.2 seconds.
Yeah.
And so you need a bigger basis if the time signals get longer.
Yep.
So does that mean that if you have a very reverberant environment, that you need a larger basis?
I would think so, yeah. Yeah, that's what the results seem to indicate in these small preliminary studies.
And do you think it's more complicated if your geometry is not as simple as you have, or doesn't that matter?
I don't think that matters much.
Okay.
No.
That would be very beneficial.
Yes, indeed. And one very important kind of takeaway from this is also you see that the bigger the problem is, the more you can reduce. That's very good, because these are tiny problems, right? Yeah. What happens when we do this room, you know?
And do you foresee a problem in 3D? Because you need a result of the full model for the whole space, right?
Yeah.
So that means some storage.
Indeed, yeah. And then you need it for many parameter values.
And many time steps.
Yeah. So you can't do this on your laptop, that's for sure.
Yeah.
You need some HPC systems for this. But this, you know, the way I envision it is that you could, you know, in a few years' time, if this goes to industrial applications, you could set up your model, set up some parameters or variations, and then put it to the cloud. The cloud churns it over the night, and then you come back and say, and have the reduced model, and then you can quit. Something like that.
My last question is about the impedance dependency. So you parameterize the impedance of boundary, and then you derive the reduced order method. Yeah. So the basis functions, are they different for the different impedance values, or is it one set of basis functions?
One set of basis.
And I could not see how you finally calculate for a certain, if you would select, okay, I want to get the result for this impedance.
Yeah.
How you would apply the model, that was not so clear for me.
Okay, yeah. So you need, I mean, in the data that you collect, you need to collect for different impedance values. And then you need, you know, if it isn't in the snapshots, the information, then of course it isn't in the reduced model, right? But if this variation of the parameter is in the snapshots and in the data that you do the SVD on, then you can go, then the basis covers that, so to speak. So it's also maybe if you look at, or at least for me, I think it's most clear if we look at this algorithm here. So we do first, you know, for single parameter value, we do gather snapshots for that time trajectory. We do an SVD of that, and we then add that to a big snapshot matrix. And we do this for all the parameters, so we adding the snapshot matrix. And then we do an SVD on that snapshot matrix. That's the reduced basis that covers.
Okay, but then when you call the result of one impedance value from your reduced order method, how are you doing that?
How to do that? It's been a while.
No, it's not so long ago.
Not so long ago, but still long enough for it escapes my mind. But yeah, shall we look at the code afterwards?
Yeah, sure. So I gave opportunity for Peter and Jonas to ask their last questions.
I can say just a few words on this. I found this last paper really nice and inspiring.
Okay.
Yeah.
So happy to hear that. I'm also personally almost most excited about that.
Yeah. I mean, it's pointing forward in a good way.
Yeah.
I can also, I mean, it's also links to other things we have been working with.
Absolutely. Yeah.
If I just should have one question here, is really so you take the time as being one of the parameters.
Yeah.
And then you use this the POD method, the regular grid.
Yeah.
Is it really necessary to treat time as a parameter? Couldn't it be part of to put it together with space?
Right. Yeah, maybe.
And then
So, yeah, I think that's a possibility. But to my understanding, at least the sort of standard approach is to treat time as a parameter.
Okay. Because you have not really any use of that.
No.
Because I mean you can just use it for interpolation between the times.
Yeah, exactly.
And you say that also that
that's
actually meaningless.
Yeah, exactly.
But then you're using this very clever greedy algorithm, or using Gaussian process regression on the error measure.
Yeah, exactly.
So that's everything.
Okay. Peter?
Okay, I don't have any questions on paper 8. That was nicely covered by Martin and Jonas. Should we try to, now I can see that we have only 2 minutes left. So could I ask the administrator, is it so that at 12 o'clock sharp that Zoom will be shut down?
Pretty much.
Pretty much.
You can have a few more minutes. I think we started a bit.
Okay.
Yeah, but not much.
Okay, I would. I have one question. I think that is that I think you would agree that these very accurate methods, they have to be combined with other methods for higher frequencies in hybrid methods. So the big challenge is this, I think, in geometrical acoustics, which is obviously efficient for medium and high frequencies. How do you do to do a hybrid with a method which still has problems for certain phenomena at high frequencies?
You mean the geometrical acoustics have problems in high frequencies?
Yes, they could be cases, for instance, as you mentioned the diffraction at some point that can still be a problem for certain geometries. In many rooms, it's no problem, but in other, they could be.
Yeah. So
what can we do to solve that? Because your method, I think, will still be too expensive to use for high frequencies in large rooms.
Yes, I think that's fair to say. Let's see how far we get with model order reduction, but still full spectrum large spaces is I think going to be a challenge. So I mean, I guess there's also ongoing work on geometrical acoustics. I think that when they did the round robin last year, they pointed to two things which were caused. Then they were only assessing geometrical acoustics algorithms, and they pointed to two things. There was the lack of diffraction and the lack of accurate boundary modeling. So perhaps there's some room for improvement, particularly in the high frequency range, in the boundary modeling of geometrical acoustics methods.
And maybe it could be possible to use hybrids where an accurate method is used for a part of a volume in a room where it's particularly challenging, but to combine with geometrical acoustics.
Yeah. Also, you know, hybridize across time, not just frequency. So you do a more accurate method for the early portion and a less accurate for the late portion.
Yeah. So we still need some to put all these parts together.
I agree.
I'll let Martin and Jonas have some final comments as well.
Any comments? We might need better models for diffraction, Peter.
Okay, I hear you. I hear you.
Oh, that was a joke. Actually, I don't have any more comment.
Okay.
Just thank you very much for your great answers.
And thank you for the great questions.
Yeah, same for me. I'm very happy.
Okay, excellent.
Okay, so now the committee has finished asking questions. Time is up, which means that we won't have time for any more questions, even comments from the supervisor. That will have to be done after the session. So now this defense is finished. Thanks everybody for participating, especially Finnur. Now the committee will discuss and submit the recommendation to DTU. So I guess we should agree on a time when we can present the verdict. What do you think will be needed?
Do we need half an hour? Probably a bit less. No longer than half an hour.
And then we meet again there, or in the Zoom, or how does it?
Yeah, then we meet everybody in Zoom again.
Yeah.
Let's say then half past one.
Yeah.
Yeah.
Yeah, that's all.
Sorry, yeah, half past.
Yeah.
I got mixed things.
Yeah.
And then I guess that you go to the lab, and then we also come there and
Yes.
announce this.
Okay.
Right.
Yeah. So there is a small reception there outside the acoustics building now.
Good. So see you there.
Yeah.
So Peter, I just created a Teams link that I sent by email.
Okay.
He needs to leave. I should run to the toilet. But let's see if you have got the.
Martin, just to tell you, we have some sandwiches for you over there. So thanks a lot. That's for your lunch. And maybe we start.
Yeah. But it's 6, so I think I would be comfortable being around.
So hi Peter, I see you. So then I will.
Yeah, so if we can meet at 1:30.